Y'all ready? Everybody ready? Yeah, we're going to do the test early. We're going to do it today. Everybody ready?
It's open book, right?
It's, yes, you can open, you have a history book or something like that, you can use that. You and your imaginary friend. Okay, so look, we're going to get into 6.6 today, improper integrals. And there are two types of improper integrals that we're going to deal with. Let's see how much we get through today. My hope is that we can get through both. I doubt it, though. So let's not waste any more time. I've already started class late. I apologize. So type 1 are called infinite intervals. So the idea here is that instead of looking at the area underneath some curve between two finite points A and B, which we would consider A and B to be a closed interval, right? We now want to make this interval infinite. And there are several ways we can do that. We can start, so this is a closed interval. What's an open? How can I make this an open? Parentheses on each? That would mean don't include the endpoints, right? So that's a closed interval. If I have an infinite interval, what I need are one of the endpoints, at least one of the endpoints to never stop. So I can go from A forever to the right, or I can go to the left forever and stop at some point, which I will call B. Or I can go out both directions forever, which would be that situation. Okay, those are the three types of infinite intervals that we can have. And the notation we have for each of these when we're dealing with integration is given right there. So when you have this situation, your integral will go from A to infinity. Here, this integral will go from negative infinity to B, and then this integral will go from negative infinity to infinity. So our limits of integration will change to one of these three formats in the event that we want to evaluate the integral on this infinite interval. That makes sense? Just note, this is just notation. The big question is, how do we actually compute these? Like, how do you find the area underneath the curve that never ends, right? That just keeps going. So here's the definition. So we're going to start with the first type, which would be this interval A to infinity. So by definition, this is the way we define it. The integral from A to infinity of some function f of x dx will be equal to, what we do is since A is fixed, we don't change it. We just leave it alone. And instead of using infinity up there, we just call this upper limit of integration t. And what we're going to do is we're going to take a limit as t goes to infinity of f of x dx. That's the definition of the improper integral or this is an improper integral. This is its definition if your interval looks like this. Now, if your interval looks like this, then what we're going to have to do is replace the lower limit of integration with t and let t go where? Negative infinity. Okay? So let's see. Let's follow the notes here, though. This is a picture of what's happening in the first situation, right? So in this particular picture, what would A be in this picture? A looks like it would be 1, right? It would go from 1 to infinity. And so we would be interested in finding the area underneath that curve. So this is the second definition. I don't think I'll write all these on the board. But do you see how we replace the negative infinity down here? We replace it with t, right? And we let t go to negative infinity. And then that's the picture for that situation. Got it? Then the last situation would be if we have it on infinity on both directions. And to do that, I forgot to say this. Because these integrals, right, because both of these integrals involve limits, from Cal 1, do you remember the idea that a limit could converge or diverge? These answers, no? Huh? Okay. Converge meant that it went to a number. Diverge meant that it did not. Those were the two things. Let me give you an example of some limits. Limit t goes to, let's say, infinity of 1 over t. What does that limit do? It converges to 0. Right? Because as t gets bigger, this ratio gets smaller, it approaches 0. Yes? So that converges. Here's another limit. Limit t goes to infinity sine t. We would say it diverges. And the reason is because if you were to actually go out on the sine curve, it just keeps oscillating back and forth, so it's not going to any particular number, right? It's just keeps going between -1 and 1, -1 and 1. So this limit right here would diverge. This one converges. And that's what we had for limits in Cal 1. They were either convergent or divergent. And what I'm saying now is since we're defining this integral to be a limit, this integral will either converge or diverge because it's a limit, right? All right. Lastly, we have if this last case where we're using the interval from negative infinity to infinity. Whenever you have this situation, what we have to do is actually split the integral up into two pieces. So look at the way I did this. We go first from negative infinity to a, and then from a to infinity. So it's like you're stopping it somewhere. It does not have to be in the middle. You're just stopping it somewhere and creating two integrals from it. I'll draw a picture. Let's say we had a function that did this. Right? And I wanted the area both directions forever, right? What I would do, if I wanted to find the integral from negative infinity to infinity, if I wanted this, is I would split it up into two integrals, negative infinity to a. A could be any number in here. Doesn't matter where it is. I could pick it right here, a. Right? And I go from negative infinity to a, whatever that answer is, plus the integral from a to infinity of the function. So that's just, we basically have made two integrals, which means two areas, right? The first integral gives you that, right? And the second integral gives you that. Yes? But that's the way you have to do it, all right? And look at each of these, the red one and the blue one. This red one means you have to do a limit, right? Limit t goes to where? Negative infinity t. So you have to rewrite that as a limit. This one, you have to do a separate limit. Limit t goes where? To infinity, and then rewrite it. So these two are examples of the previous case, aren't they? The previous two cases? We just put those two together into one answer. That make sense? Okay, let's take a look at these examples. So find this. So when we're doing improper integrals, remember I said there's two types, right? Two types. Infinite intervals, which is what we're doing now, and then the second type we're going to do later if we have time. Because of what we have to do later, I'm going to tell you to do something right now that will help you in the big picture of things. Okay, so whenever you see an integral from here on out, when you have limits of integration, whether they be numbers or there's infinity in there, it doesn't matter, always pay attention to your domain. What is the domain of this function? What is the domain of the integrand? What is the one thing you cannot have? Zero, right? So let's just keep that in mind. I'm going to draw a little number line over here. Here's 0. That cannot be in there, right? But what interval am I looking at? 1, right? Here's 1 out forever. So am I concerned at all about that 0? No. Okay? Later on we will be, because we might do an integral. Like what if I did an integral from -1 to 1? Then wouldn't that 0 be a problem? And we'll deal with that. That's type 2. So let's just get into the habit now that whenever we have definite integrals, that we pay attention to the domain and make sure that any domain points are not within our interval of integration. Understand? Okay, so we're okay on this, right? We're check okay? All right, so this is an infinite interval. So I'm going to convert it to a limit. I'm going to let t go where? Positive infinity. And I'm going to do integral 1 to t, 1 over x squared dx. And we all know, because we're going to take a test a week from today on integration, we all know how to integrate 1 over x squared. So I don't do anything with this limit, all right? Just keep it out here. Just continue to write it, okay? Don't just lose it. I mean, bring it with you. What is the antiderivative of 1 over x squared? Negative 1 over x? Negative 1 over x? And we're evaluating that from where to where? 1 up to t, right? Like this? So what I've done is, I'm focusing all my attention on this, right? That, using the fundamental theorem of calculus from last class, says, oh, find the antiderivative of this, which we did, and then draw this bar and then plug in your two endpoints. So now I've got to actually do this. Plug in t, plug in 1, right? Let's do that. Let's plug in t. So limit t goes to infinity, bracket. Okay, so I have two things. Okay, plug in t, I just get negative 1 over t, right? Plug in 1, I get negative 1. I guess we could clean that up a little bit, but I think we're ready for the limit. Let me see. Go one more line. Limit t goes to infinity of negative 1 over t plus 1. We agree? Now that you've done all the integration, you've plugged in, you've kind of cleaned it up, now let t go to infinity. So what happens if t goes to infinity here? That goes to 0 plus 1. This integral converges to 1. That means that if we were to graph this, right, 1 over x squared, which I hope you know looks like this. That if you were to start at 1 and start looking at this area forever, that area would converge to 1, which means that it's never going to be bigger than 1. Right? So if I were to go out here, let's say x is 100, what I could tell you is that answer is going to be less than 1. If I go out further than 100, if I go out to 1,000, it's going to be even closer to 1. If I go out to 1 billion, it's going to be even closer to 1. And if you could continue to go forever, which you cannot do, but if you could go forever, then it would be the number 1. That would be the area underneath that curve. Understand? Yes? Here we get into the idea of, can you actually go forever? I mean, we couldn't do it, right? But conceptually, the idea is that the further we go out, the closer and closer and closer the answer gets to 1 without ever getting to 1, because you can't ever get to infinity. All right. Let's look at the next one. Change the problem up just a little bit. 1 over x. This one will go quick. Same interval. And I'm going to convert that first to a limit. I'm going to let t go to infinity. Integral 1 to t, 1 over x dx. That's just the definition of the improper integral, right? Now what? Yeah, we didn't do a number line. Is 0 in here? I should have. 0's not in there, so I'm not worried. Okay. Take the antiderivative, right? What's the antiderivative of 1 over x? Natural log, right? So don't forget the limit out here, though. This is natural log of the absolute value of x, right? Evaluated 1 to t. Now you plug in t, you subtract what you get when you plug in 1. So this equals limit t goes to infinity of, okay, so plug t in first, you get natural log of the absolute value of t, right? Plug in 1, you get natural log of 1, which is 0, right? Natural log of 1 is 0. And this now equals the limit as t goes to infinity of the only thing left, natural log t. So what is that? It goes to infinity. So you just have to remember what the natural log function looks like. Natural log looks like this. And this is natural log of x, right? And so what we're saying is what happens to the natural log function as we let the argument get bigger. So that would mean like let the number inside get bigger. You can see that the graph of this goes up. It's slow growth. It's logarithmic growth. It's not as fast as like exponential growth, but it is growth nonetheless. So it'll continue to go up forever. So this goes to infinity, right? This goes to infinity. Therefore, this integral diverges. And that's the answer you want. It diverges. I'm only putting the arrow to infinity just to let you know that that became infinite. It's not going to a number, right? It's not going to a number. So the integral diverges. Yes?
On the test, you're going to have us do the right diverges or converges?
Yes. Well, if you give me a numerical answer like the last one, 1, then I'll know it converged. But if you get something like this, you need to state diverges. We good? Look at the next one. Recognize that? Oh, I want to go from negative infinity to infinity. So sorry. Do we have any domain issues?
Yes.
Anything that's going to cause the denominator to be 0? No, right? Can't make the denominator 0. This is going to be the smallest number this could ever be is 0, right? Can never be a negative, and then you're going to add 1, so the bottom can't be 0. All right, so no domain issues. That's a good thing because I'm integrating over the entire number line, aren't I? So how do I do this? Break it up. I go negative infinity to where? You can go anywhere, right? Your choice. You can go anywhere between negative infinity and infinity. You could pick 10. You could pick pi. You could pick any number. So let's pick 0. 0 is always fun. 0 is always easy to plug in, isn't it? So we're going to do that. And then we're going to go plus, right, a separate integral that picks up where we left off, which was 0, up to infinity, and then 1 over 1 plus x squared dx. What now? What do I do? What is it? Limit. We need to do a limit on this. Figure that out. And then we're going to do a separate limit on this one, right? So this limit's going to look like this. Limit t goes where? Negative infinity of integral t to 0, 1 over 1 plus x squared dx. Plus this one. Limit. And we can use t again. It's all right to use t again as long as you understand these are two separate problems. T goes to infinity. Integral 0 to t, 1 over 1 plus x squared dx. Now the good news is that these both have the same antiderivative, right? So you only have to find one antiderivative. It's the plugging in stuff that you have to do differently on each one, right? All right, so let's do this. This is going to become the limit as t goes to negative infinity of arctangent of x evaluated where? On the bottom it's what?
Negative infinity.
Not yet. T and the top 0. So we've got to figure that out, right? Sorry, I'm trying to keep this up high so you can see it. This is my line right there. And then plus limit t goes to infinity of arctan x, this little bar, 0t. Notice that as I'm writing this out, and I started here, I split it into 2. Each of these I wrote a limit in front, and I'm continuing to write the limit the whole way. Your notation needs to be like this. You can't just like have limits appear and disappear when you want them to. It needs to be like a sentence, you know, like one line equals the next equals the next. It should all make sense. It shouldn't be just like scratch work in your head randomly thrown on paper. All right, so just try and get organized in the way you write it. Yes? Okay, so my next line, all I'm going to do is I'm going to find out what's happening inside these brackets, which means fundamental theorem of calculus, 0 in here, t in here, right? Subtract. T in here, 0 in here, subtract. All right, so let's do that up here. The limits are going to be sitting out in front of all those. So we'll have limit t goes to negative infinity, bracket, parenthesis, parenthesis, minus, parenthesis, parenthesis. So what would happen if I plug 0 in here? Arctan of 0. 0. Remember at the very beginning of class we talked about inverse trig functions? Okay, so you need to understand inverse trig functions now. Arctangent of 0 is 0. Yeah. What is the angle that gives you 0 in the tangent function? All right, now plug in t. You just get arctan t, don't you? All right, plus now another limit. Limit t goes to infinity. All right, plug in this time what first? T. So you get arctan t. And over here, plug in 0, you get 0, arctan of 0, 0. Whew. All right. Almost done. I guess you don't need the next line, but I'll write it down. I'm just getting rid of those zeros. That's, okay, that's what we have, right? That's it. So we're trying to let t go to negative infinity right here. Arctangent, and then this is trying to become negative infinity. So the best way, I think, to look at this is to go back and think about not arctan, but the tangent function itself. What does tangent look like? Yes, but when you graph it, doesn't it look like this? And it has these vertical asymptotes, doesn't it? And they happen at pi over 2 and negative pi over 2. Yes, we would have another one at 3 pi over 2, but I'm going to go backwards because arctan, we only look at this one, this restriction. So back when we said what was arctan of 0, y'all said 0, right? That meant where on this function do I plug in, do I get a 0 output, right? Where is my output 0? At an x coordinate of 0. Now when I say what's arctangent of negative infinity, I'm saying where on the x-axis is my output negative infinity? This way, right? You have to actually let your x value approach what? Negative pi over 2. Now you can never be there, right? But this is a limit. You're allowed to do this if it's a limit. So what I can tell you is that this right here is approaching negative pi over 2. But be careful, there was a negative in front, wasn't there? Okay, so what I have from this first limit, everything here is negative pi over 2, or minus negative pi over 2. You okay with that? What about this one? Arctangent of positive infinity. So you go over here and you look and you say, where do I get a positive infinity? Right here. Pi over 2, right? So this answer is pi over 2. Add the two together. Pi over 2 plus pi over 2 is pi. The answer is pi. You're converging to pi. So if we were to graph that function, if we were to graph 1 over 1 plus x squared, I think we did talk about that graph last class a little bit. If we were to graph it, it would look like this. At 0, it would be 1, and then it dropped down. Like that. That's what it kind of looks like. Like what? I'm sorry. Someone say something? Okay. If we were able to go out in both directions forever and find the area underneath that, the area would be pi. Okay? Does that look like something that anyone that you've seen before in your life, that sort of curve? Bell curve. That's right. How many of you have heard of that's a bell curve? Y'all heard that before? Bell curve? It's actually, the bell curve comes from has a more technical name. It's called the standard normal distribution, which is a bell curve. And what it tells you, I mean, most things in the real world follow this sort of behavior, meaning that in the middle, you have kind of like your average, and then you have, as you move out in each direction, it drops off. So let me give you an example. Let's just take the height of men, right? And don't worry about the fact that this is 0. We can always shift this over left and right, okay? But if you take like the average height of men, we're doing men and women separately, right? So the average height of men, you would have an average which would be in the middle, right? Then you have, people who are above average and below average as far as heights. And so, this might be You raising your hand? Yeah. No? Okay. So I don't know what the average height is. 5'10". Okay, so 5'10". I don't know. 5'10", 5'11". Okay, that's the average, right there. Okay, and then you have something like 6'3" over here. Maybe that's there's less probability that a person's going to be that tall. Then you have over here you've got some 7-footers playing in the NBA, right? And then you have the 10-footers, the 10-foot 3-inch men. Has there ever been someone that tall?
Yes.
Yeah.
Tallest is 11 foot.
11 foot. So there's a probability that it's possible, right? It's possible. Now, what about that 232-foot man? So there's never been a 232-foot man as far as we know, right? Can you say that the probability that it would ever happen is 0? Can you say 0? You can't say 0. Okay, so remember this is probability, right? Yeah, you're right. They're going to have a lot of issues, right? But let's just say that when it comes to theoretical, right? When it comes to theoretical, you cannot say the probability is 0. You can't. The probability of a person being 232 feet tall, the odds of that happening are probably less than the odds of you winning the lottery every single day for the rest of your life. I mean, could you win the lottery every single day for the rest of your life? Could you go play the lottery and win every single time you play for the rest of your life every day? Could it happen? Could it happen? Okay, you can't say it can't, right? That's what we're talking about. We're talking about this is diminishing out to 0, isn't it? It's really small. So small, in fact, that it might be that, this is just what we would logically say is impossible, but you can't say impossible. So these distributions this is the way almost everything behaves. It's called the law of large numbers. If you have a large enough n, a large enough sample size, almost everything is normally distributed. Just about everything. All right? Which is why when I get your grades on a test, and they look like, this is 100, and this is 0, and the grades look like this, that's an inverted bell curve. That's flipped over that, and that's not good because you've got a lot of stuff over here, a lot of stuff over here. Your average is in the middle, but you're not normally distributed. Do you understand that's not normal distribution? Average would be in the middle, but as you move out, you actually get more probability than smaller. All right, so these functions are actually very, very useful. They're used in statistics all the time, and they are called probability density functions. And the property of a probability density function is this. To be a probability density function, you must have this property. Now, this is not in the book, all right, so I'm just kind of going off on a tangent here. A probability density function, not a PDF, Adobe PDF file, okay? I just don't feel like writing probability density function out here. A probability density function has this property. The integral from -infinity to infinity of that probability density function must be equal to 1. That means that the total area underneath the curve must be 1 in order for us to classify it as a probability density function. Now here's why. Each of these represents a probability, right? So what's the probability that you're going to be 5'10"? Pretty good, right? What's the probability you're going to be 6'3"? Not so good. What's probability you're going to be 7 foot? Rare, right? Okay. The total sum of all the probabilities should be 1. Just like when you have a coin, what's the probability of flipping and getting a heads? 50, so 1/2, right? What's the probability of flipping and getting tails? 1/2, right? You add the two 1/2s together, you get 1. So if you take the sum of the probabilities of each event, add them up, you have to get 1. That's the universally accepted thing when it comes to probabilities. So for this to be a probability density function, the area underneath it needs to be 1. So was the problem that I just gave you a second ago, is this a probability density function? Could you make it a probability density function? How? There you go. Now it is. Right? That's it. So if you take that, we know that's pi. Scale by 1 over pi, it's now 1, isn't it? Now that's probability density function. So those of you who ever take statistics and take statistics that involve some calculus, you'll learn about the standard normal distribution. And the function in here has these weird scalars out in front, like 1 over 2 pi and all this weird stuff. And you're like, where the hell do all these weird numbers come from? It's actually just what we need to scale by to make the area 1. FYI, you might run into that later. All right, what's next? Let's try the next one. Integral. Let me let you get started on that. I'm going to let you just quickly, when I say quickly, let's say 5 minutes tops, just at least find the antiderivative. If you can write it all nice, that's good, but you're going to need the antiderivative of this, so I'm going to give you a second to do that. Please remind me to unmute my microphone when I come back. Yesterday in my class, I forgot to unmute it for like 10 minutes, and I lost a bunch of audio. I unmuted it. I'm going to work it out while y'all are working it on your own. I did. Thank you. You won't need the plus C. That's my scratch work on the side. Force of habit.
Better to leave it like you had or to factor the e to the x out?
Oh, you can do either way. It's your call.
What's cleaner or easier in your mind?
I think at this point where I am right now, I'm not even really thinking that. I think on the next step, I might actually consider factoring it. I don't know. They're both going to get you to the same place, so. All right, let me run through this real quick. Have y'all looked up here? Y'all see what I've done? Have any questions? I split it into two integrals. I went to 0 again. I also kept in mind there were no domain issues here. E is defined everywhere. X is a polynomial. It's defined everywhere, so we're good. Split it up. Then I have to create limits for each one. Here they are. Then I'm going to need the antiderivative. So I went over here and I did scratch work in blue, and I had to do integration by parts, and I found the antiderivative, ultraviolet minus voodoo. Got that answer, threw the C out because I don't need the C for a definite integral. And why don't I need the C? Because if I put C in here, then when I plug in 0, I'm going to have plus C. And when I plug in T in there, I'm still going to have plus C. And when I subtract the two, the C's cancel. That's why you don't care, all right? So. All right, so I need to now plug in 0, and then I need to plug in T. I need to plug in T, and then I need to plug in 0, right? Can I proceed from here now? I need to erase some stuff. All right, so let's plug in. I still have a limit. T goes to negative infinity. So let's plug in 0. This is 0. Minus e to the 0 is 1. So negative 1. Guess I didn't need that big old parentheses for that. And then I need to plug in t. So t e to the t minus e to the t. E to the t. Plus, I have another limit over here. Limit. This one's going to positive infinity. And two sets of parentheses. Again, that's just more of a force of habit. I like to do that just to kind of keep myself in track of what I'm doing. I'm going to plug in t first. So t e to the t minus e to the t, and then plug in 0, I get negative 1 again, right? At this point, I'm not going to rewrite it all. I'm actually going to think about what's happening. What happens? Well, you know what? This is negative 1. Nothing's changing, right? When I plug in negative infinity into here, I've got some issues. So I think that part, just by itself, I'm going to just look at over here in blue, is like its own problem. It's like you were back in Cal 1 and someone said, hey, what's the limit as t goes to negative infinity of t e to the negative t minus, t minus e to the t. The what? Okay, can we discuss this? All right. T is going to negative infinity. Where does this go then? Negative infinity. Times e to the negative infinity. What the hell does e to the negative infinity mean? Well, that means you better know what e looks like. What does e to the x look like? Exponential function, it looks like this, doesn't it? So if I let the x get really, really big, positive, it goes there, right? But I'm letting the exponent get really, really big, negative, right? Which means go that way. Where does that go? Where's your function headed? 0. Understand? That goes to 0. Minus, this goes where? Same thing, 0. Do y'all have any questions? This is the time to ask. This is just 0. What is this? What's something that's headed to negative infinity times something that's headed to 0? 0, negative infinity? I need my...
You have to evaluate differently. You have to make it.
I'm waiting for, I'm hoping one of my Cal 1 students will bail us out here. You need to do something with it. You're going to have to get this to L'Hopital. This is an indeterminate form. When you have something that's getting really big, negative, right? Negative a billion, times a number that's getting really small. See, we're not saying it's 0, right? We're saying it's approaching 0. This is a limit. This gets small. Does E ever get to 0? No, it never gets there, right? So you got a really, really tiny number times a number that's getting really, really big but negative. And when that happens, you don't know who wins. So you've got to do something else. So you got to get L'Hopital involved here. And yeah, you got to take one and drop it down. Very good. So, all right. So I've got to investigate this further. All right? So since I'm investigating it further, I'm just paying attention to this piece right here. This piece, I'm checking that off. I know what that does. So I'm looking at the limit as t goes to negative infinity of t times e to the t. I've already said that this has the form of infinity times 0. I don't care if it's negative infinity or positive infinity. I've got a big number times a really small number. And whenever we have that, what we do is we take one of the two factors we get to choose, and we drop it to the denominator. Now, you can't just drop it. You're rewriting it. So watch. If your L'Hopital in Cal 1 was kind of weak, then this is going to be a problem. All right. E to the t over what?
T to the negative 1.
T to the negative 1 or 1 over t. So this is the same thing, isn't it? Isn't t on top the same as 1 over t on the bottom?
Yeah.
And you might be asking yourself, well, why in the hell would I do that? Because this. What happens as t goes to negative infinity now? What does this go to? What did we say that went to already?
0.
We said that went to 0, right? What does 1 over t go to as t gets really, really big? That 1 over a really, really big negative number is going to go to 0. So now instead of looking like infinity times 0, we actually have something that looks like infinity, 0 over 0. And that's what you need in order to use L'Hopital's rule. Show of hands again. How many of you did not see L'Hopital's rule? Okay, you're going to have to find some way. I know I do have some videos. Didn't I send out some links earlier this semester about go back and watch these in email? Did I not?
You said they were out there. You didn't send them.
Okay, I'll try and remember. Someone who's like freaking out about L'Hopital, send me an email and say, I'm freaking out about L'Hopital. If you could send me an email, I will send you links to my videos from Cal 1 where I actually do L'Hopital's rule. All right? Okay, so now, at this point, okay, I'm still not done. What L'Hopital's rule allows me to do is take this, and I have to let everyone know I'm about to do L'Hopital's rule, so the book does it 2 different ways. Books do it 2 different ways. Some of them do an H circled to let everyone know you're doing L'Hopital's rule, or if you took me for Cal 1, I do an L for L'Hopital. Because L'Hopital is actually spelt like this. It's La Hospital. It's La Hospital, but it's L'Hopital. All right? So what is the L'Hopital's rule again? What do we do?
Take the derivative of
So
the
you keep the limit, right? Exactly the way it is. But you take the derivative of the top and bottom separately. So what's the derivative of e to the t? Itself. What's the derivative of 1 over t? Nope, that's antiderivative. Negative 1 over t squared.
How do you let it go?
Try it again. Let t go to negative infinity. What happens? This goes to 0. This goes to 0. Shit, that's the same thing we just had. So we could do it again. Let's think about what would happen if we did it again. The top would go 0, and the bottom, the derivative is going to be something like
But would it matter?
positive 2 over t cubed or something like that. It just keeps on doing the same thing. So what does that mean? L'Hopital sucks, it's not worth it? It didn't. It means we might have dropped the wrong thing. Remember, we dropped t down, right? Why don't we...
So we drop e to the t down.
What's that?
You drop e to the t down and just
What's negative infinity?
There's no rule. Whenever you have this form, there's nothing that tells you which one you have to drop.
you just have to try.
You just have to try. We tried this, and it looks like we're getting the same recurring thing. We keep getting 0 over 0, 0 over 0, 0 over 0, right? So let's go back. I'm just going to say, Let's go back, and let's now go back to this, and let's drop the other one down. If I drop the other one down, let's see what happens. So I would drop the e to the t down and leave the t on top. When I drop e to the t down, it becomes e to the negative t. Agreed? Yes? Now what's the form that we have? Now be real careful with this. T is going to negative infinity, so the top goes to negative infinity, and the bottom, does it go to 0 still? It goes to positive infinity because look, it's negative t, and you're plugging in negative infinity, right? A negative and a negative in here is going to be positive, so this is e to a big number, which is a big number. That's going to infinity now. Now you have infinity over infinity. Can you use L'Hopital with infinity over infinity? Yes. It has to be 0 over 0 or infinity over infinity. And it's okay if it's plus or minus. That doesn't matter. So I'm okay to use L'Hopital. Here it comes. L'Hopital again. What's the derivative of the top?
1.
I like that. What's the derivative of the bottom? Negative e to the negative t. Chain rule, right? Derivative e to the negative t is itself times derivative of what's up there, which is negative 1. Now let t go to negative infinity. What does the top do? It's just 1, right? This is headed to 1 over, and then try this again. Negative infinity in here, negative is positive. That thing's going to blow up, isn't it? Yeah. It's going to become a huge negative number. What's 1 over a huge negative number going to go to? So this is basically going to go to 0.
That's just the first one, right?
That's just the first one. Got it?
So that answer was 0?
That was 0. So there would be some scratch work on the side, obviously. So I've erased where I was. I had this. I was here, right? I was working on this one. And I said, this was negative 1, right? This right here is just negative 1. And then I have minus, and then we all had agreed that went to 0, right? And then this one, we just said went to 0. Yes? Okay, so minus 0. Bam, done. Plus. Now this one's not going to be as bad. Oh, yes it is. Sorry, I thought we were good, but we're not. So let's take a look at this. If t goes to infinity, this is not affected at all, right? So I'm just put negative, can I just put plus 1 over here? Negative, plus? This is the question mark, right? What happens to that? So maybe I should work that out on the side because it's not obvious. What's the limit as t goes to infinity of t e to the t minus e to the t?
Infinity times infinity minus infinity?
T is going to positive infinity. This is going to go to infinity, right? E to the infinity. Infinity. Infinity times infinity is infinity. That's okay. It's getting big. Minus, though, infinity. And what's infinity minus infinity?
You don't know.
We don't know. It's just like 0 times infinity. You don't know. So with L'Hopital's rule and these limits, if you go back to Cal 1, there is these things called indeterminate forms. It's where you don't know what the answer is. This is an indeterminate form. Does anyone remember how you handle whenever you see infinity minus infinity? Not L'Hopital. You try and factor. You try and factor. So can you factor?
Yeah.
It was your suggestion to pull the e to the t earlier, wasn't it? So I can pull an e to the t out, right? Can't I? Let me pull an e to the t out of this. No. I'm just going to take this expression right here. Yeah, can you factor infinity out of infinity, please? Pull out an e to the t. What would I be left with there? T minus 1. Now that may seem like, okay, big deal. That really didn't do anything. But now do the limit again. Let t go to infinity. What's e to the infinity or infinity times what's infinity minus 1? Infinity. What's infinity times infinity? Infinity. That's okay. So that's infinite, isn't it? So this right here goes to infinity. Which means this goes to infinity, doesn't it? And as soon as you see that, it's over. This integral diverges. Because it has to go to a number for us to say convergence. If any piece of this goes to infinity, it's done. So that integral diverges. The integral from negative infinity to infinity of x e to the x dx diverges. No, diverges. That's all you say.
If we just put like diverges, would you get back?
Oh, it just like a flip of a coin? Oh,
After all the work, would you?
Not like instead of writing,
Like if we had
just
all
write
that.
diverges. You don't
Like if we
even.
did all the work and
If
we
we
just
don't
put
write the
diverges,
original
would you
problem, it diverges.
you mean if you don't rewrite it?
Yeah.
Oh, yeah, no, that's okay. But you need to have this stuff. You need to justify your work. You can't just go to, your calculator and do it.
I don't know how to do it.
I think on your calculator, it'll probably say infinity if you have like a T89 and you try and integrate this. Did you know your 89 you can change your limits of integration to be infinite?
I don't know how to do that. But
Well, there's an infinity key.
I know the infinity key.
You just you don't know how to do the integral.
You get into my integrand because you have to do integrand, something.
Integrand, comma, variable, comma, lower limit of integration, comma, upper limit of integration. So it'd be like x e to the x, comma, negative infinity, comma, infinity. Enter. That's what it would be. That's it.
Did you get a chance to look up the Eureka program?
Uh-huh.
It'll explain why you're so angry.
Oh, yeah? Okay.
You guys use a computer to get a bunch of equations that we've never discovered in science before, but they work really good in bio.
Uh-huh.
Now this whole team is trying to figure out why this answer works and what the hell these variables are.
Eureka? Okay. All right, so as you can see from this, this is going to fall back on Cal 1 stuff, right? I'm going to assume that you do remember some limit stuff. So get brushed up on it. When you go through your homework, you'll be challenged with that sort of thing. Pardon? It says infinity? Yeah. Okay, so a quick little formula for us. If we ever take an integral from 1 to infinity of 1 over x to the p dx, then this will be equal to one of two things. It'll converge if p is greater than or equal to 1. It'll diverge if p is less than 1.